Let's start today with a practice problem. This question asks you to think about the solvolysis of 3-bromo-2,2,4-trimethylpentane in ethanol. And so that's this compound right here. And you want to draw the major product of an SN1 solvolysis mechanism. So at this point you should pause the video and try to show that mechanism and that major product, and then restart the video when you're ready to see how you did. Let's see what you came up with. Well, in an SN1 mechanism, the first thing that you would expect to occur is the loss of the bromine as a leaving group to form a carbocation. This is a secondary carbocation, and when you see an SN1 solvolysis of a secondary alkyl halide, you expect for any secondary carbocation to shift. If we look to the right-hand side, there is a hydride group that can shift, and the left-hand side also has a methyl group that can shift. That's one of the points of this particular question, was to answer the question of which should I shift, a hydride or a methyl? And the answer is that the methyl groups take longer to move over on a carbocation than a hydride. So as our major product, we would expect that hydride shift to occur. The hydride slides over, that forces the carbocation over to this tertiary position. The hydrogen is still here at the secondary position. I just didn't bother to show it because it doesn't do any additional chemistry. SN1 means there's a substitution, so in the next step, the ethanol, which is our solvent, will attack that carbocation, and we end up with an alkyl oxonium ion, and then a final deprotonation step where the ethanol is most likely to come along and pluck that hydrogen off. You could show a bromide doing the same chemistry here, but ethanol is the solvent, so that means it's everywhere. So it's more likely to do that than a bromide, and the ethanol is a stronger base. So this right here is the major product that you would expect at the end of this SN1 solvolysis reaction. The functional group that's found in this product is an ether, and we have not learned how to name ethers, so you can stop here with just the drawing of your final product. One of the themes we're going to see show up again today is the idea of what happens to the chiral center. So this carbon right here started off as a chiral center. The chirality is going to be partially scrambled just by the formation of the carbocation. And then when the carbocation does form and it moves over with the hydride shift, now this is no longer a chiral center. So we go from a chiral starting material to a product that has no more chiral centers. And so this is an achiral product. So we lose the chirality, and that's why I didn't bother to specify if the reaction started off with an R or S, 3-bromo-2,2,4-trimethylpentane. As far as minor products go, there's actually a competition that can occur. So the alternate shift does occur to some limited extent, and this is actually a foot race that occurs. Will the hydride shift faster or the methyl group? And the majority of the time we would expect the hydride to shift faster. So this still represents my major product. This methyl group shift would represent a minor product. And then we'd see the same final two steps where the ethanol jumps onto the carbocation, and then something has to come along and deprotonate the ethanol. So these two ethers that we end up with are different ethers, and the black pathway right here represents the better pathway, the major product formation. The red pathway represents a minor product. An even more minor product would be if no shift occurred at all. So what happens if the ethanol just captured the carbocation directly? And again, all three of these are going to happen to some extent. The black pathway represents the most probable pathway, the red represents the second most probable, and the magenta represents the least probable of these three pathways. The ethanol can jump onto the carbocation directly, and then a final deprotonation step to give us our ether. So this reaction is going to make a mess. And you should be able to rationalize all three of these different products, but we would expect the black pathway to represent the major product that follows the rules that we've been learning. This was a review of a previous idea. Let's move on to new material. So today we're going to look at these key concepts, and in the lesson you're going to need to define these concepts. I'm going to work from a PowerPoint today, and so hopefully you have the lesson printed off or accessible to you, and you can fill in the answers, but I'm going to work from the PowerPoint and still answer the same questions. We're going to introduce today not only a new type of reaction, but also a new reaction. This is called hydrogenation. And this is kind of a cool reaction that has a lot of industrial significance. If we look at our starting material, this is an alkene, which we learned how to make using elimination chemistry in the last chapter. You can react an alkene with molecular hydrogen, H2, and it will produce an alkane. Thermodynamically, this is downhill, because what we're doing is we're going to break this pi bond right here between the two carbons, and we're going to break a sigma bond between the hydrogens, and we're going to replace that broken pi and broken sigma bond with two new sigma bonds. So ultimately, we're trading out a pi and a sigma for two sigma, and this is a win. We are producing more stable bonds. Energetically, this is going to be spontaneous and downhill. But this still is a very, very, very slow reaction. And so just bubbling hydrogen through an alkene is going to take you far too long. And so instead what they do is they add a catalyst. Platinum, palladium, nickel, and rhodium, I believe is what RH is. Those are the 4 different catalysts that we typically add. And these are just flakes of metal that they swirl around with a stir bar inside of the reaction while bubbling a stream of hydrogen gas through your reaction container. The solvent, this particular reaction would probably be run in the gas phase, but a solvent typically just needs to dissolve the alkene. A common solvent is acetic acid or any of the chlorinated hydrocarbons like dichloromethane or trichloromethane or carbon tetrachloride, which they no longer use because I believe it's more carcinogenic than it needs to be a suitable solvent. This specific reaction is called an hydrogenation reaction, and it specifically involves the reaction of an alkene with molecular hydrogen to produce an alkane. It is part of a larger family of reactions called addition reactions. These addition reactions are the focus of Chapter 8, which is the chapter that we're looking at right now. The key feature of an addition reaction is that it is the opposite of an elimination reaction. In an elimination reaction, we made an alkene by getting rid of some things, and now we're going to break that alkene by adding some things to it. There are several ways of trying to describe the chemistry of an hydrogenation reaction. In organic chemistry, we like to use arrow-pushing mechanisms, but the problem is that because these hydrogenation reactions involve a metal catalyst, we can't really push our arrows that we like to push as easily. So the actual way that we show these reactions is in what's called a catalytic cycle. This is the mechanism equivalent of a catalytic reaction. Rather than dig into the full detail of a catalytic cycle, let's back up and evaluate and kind of appreciate the cartoon diagram here for what it has to show us. In the first step of the cartoon diagram, what we see is a metal surface, and this is a metal in its pure state with an oxidation number of 0. This is an electron-rich metal surface. That's what these little blue spheres represent. If you were running this reaction in a laboratory, what you would see were little slivers of these very valuable metals, but on a molecular scale, they're these massive surfaces with many trillions of atoms in all directions, essentially an endless plane of electron-rich metal atoms, and a hydrogen molecule sees that electron-rich surface and gives up the bond between the two hydrogens and sticks to the metal surface. From the hydrogen's perspective, this is a massive win. Hydrogen never gets to win the tug of war for electrons because its electronegativity value is very low, but across these metal surfaces, the hydrogens actually command the bulk of the electron density. They are overjoyed. And the amount of mass of hydrogen that you can lock onto one of these metal surfaces is often 2 to 3 times the mass of the metal itself. And when they look at using hydrogen as a fuel source for space travel, the way you store that fuel source is often on these metal surfaces, or at least that's one idea that they're exploring. This represents the alkene right here. The alkene's just kind of hanging out in this first step. And what you'll notice is that the alkene, the double bond, for whatever reason, is not shown by the artist, but you should appreciate that both of the carbons in this alkene are sp2 hybridized because of the trigonal planar geometry. So once you have the hydrogen add to the metal surface, now this metal, which currently had an oxidation state of 0, is going to take on a positive oxidation state. That positive charge actually attracts the pi bond, and it pulls the pi bond down, kind of sags on the pi bond, almost as if a hand reached up from the surface, grabbed a hold of the pi bond, and pulled it down. And now the carbons here are making two sigma bonds between the carbon and the metal surface. This is called a coordination step, and this is kind of a diagram of what that looks like. Notice that these carbons, which used to be sp2 hybridized, are now sp3 hybridized because they're trigonal planar. Sorry, they were trigonal planar and now they're tetrahedral. So we changed the hybridization of the carbons, and now everybody is loaded up on the metal surface and ready to start to do the actual chemistry between the carbons and these hydrogens. So now we move over down to the left, and in this diagram what's happening is an insertion step. And if you think about this world from the perspective of the carbon, it is sharing electron density with the metal, but it sees, almost in a fit of rage and jealousy, the carbon sees this hydrogen enjoying excess electron density for the first time in the atomic existence of the hydrogen, and so it just grabs the hydrogen and sticks it to one of the carbons and ends the joy of the hydrogen right there. This insertion step is kind of a brutal takeover of electron density by the carbon and just kind of ceases the hydrogen's short time in the sun where it actually had extra electron density. The first carbon does that in this insertion step, and then the second carbon does that in the reductive elimination step. And what happens here is the carbon reaches over and grabs the hydrogen, the second hydrogen, and then leaves those electrons behind. That's why it's called a reductive step. From the metal's perspective, when the second carbon grabs those hydrogens, those electrons go back to the metal, and the metal kind of gets its electrons back. It unoxidizes in this last step. So if you want the metal to be a catalyst, if you oxidize it in the first step, you're going to have to reduce it in some subsequent step, or you'll end up using up your metal. So that's what this looks like in a cartoon diagram. In the catalytic cycle is where we try to describe those exact same events, but we describe them with the precision and perhaps lack of user-friendliness that you're used to seeing in a typical organic chemistry idea. We see the same steps. Here's the metal with a zero oxidation state starting off all by itself. Nobody's bothering it. The hydrogen sees that metal and sticks to it. This is that oxidative addition, and it's called oxidative addition because the metal went from a zero to a positive oxidation state, typically +2 for every 2 hydrogens, but this is occurring along the entire surface of the metal, so it's kind of stupid to pretend like this is just one metal atom. But that's what we do. That's how we think about this, because we don't like the cartoon diagram. Once the metal takes on the positive charge, then the alkene will stick to that metal. That's what's going on right here. This dashed line means that the relationship between the metal and the alkene is not well defined. In the previous slide, I tried to show that as 2 covalent bonds. It's actually a little bit more vague than that. And this idea that a metal just kind of reaches up and grabs a hold of a pi bond and just sags on it is a theme that we'll see later on in the semester. Once the metal kind of sags on that pi bond, then the carbon starts looking elsewhere for electron density because the metal's grabbing it. So the insertion step is where one of these 2 carbons just reaches over and grabs the hydrogen. And so now that formalizes, instead of a dashed bond where the metal's kind of sagging on the electrons, when the pi bond is officially given up by the carbons in this insertion step, we now have a defined covalent bond between the carbon and the metal, and a defined covalent bond between the carbon and the hydrogen. The fourth step is a reductive elimination, and if you count, there are 2 electrons here, and 2 electrons right here, and 2 electrons right here. That's 6 total. In this final reductive elimination step, those 6 total electrons reduce down to just 2. 2 bonds. There are 4 total electrons. So we went from 6 total electrons to just 2 bonds with 4 total electrons. So the law of conservation of matter tells us that those other 2 electrons must have gone somewhere, and they go back to the metal. That's why the metal goes from a +2 oxidation state back to a 0. The definition of a catalyst is that it is recycled during the course of the chemical reaction, and that's exactly what happens to this metal. So a catalytic cycle tells the story from the perspective of the metal. And as long as you keep drawing that metal and talking about what's happening to it, then the organic chemist, which doesn't usually care about the metal, allows you to kind of do that. And so these are the 4 steps that are typically associated with the catalytic cycle. You should be able to reproduce this diagram for a variety of different alkenes. I'm going to practice drawing this for a few different alkenes. Okay, some details that allow us to know what happened with this catalytic hydrogenation is, first of all, when the carbons sit on the metal, they sit kind of on the same face of the metal as these hydrogens do. In my mind, I think about this much like a professional oil repair shop, where you pull the car forward and then there's kind of a hole in the ground where all the mechanics work on your car from underneath the car. And the reason that this is important is when these hydrogens are added to the carbon, both hydrogens get added to the same side of the carbon. That's what we refer to as syn addition right here. Anti-addition is where one of the hydrogens would add on one side and the other hydrogen would add to the other side. So syn and anti are opposites of each other. Catalytic hydrogenation only shows syn addition. If you go back to the carbon right here, notice how both of the hydrogens that are added to your original hydrocarbon get plugged in on the same side. More importantly, they get plugged in on the same side where the carbons were docked on the metal surface. And that's going to have some consequences. So looking at these two different molecules right here, here's an alkene. If we catalytically hydrogenate that, then both of those hydrogens get added to the same side. And I could have shown them both here as wedges or both as dashes, and it would not have mattered. One of the reasons it doesn't matter is because this new single bond right here is free to undergo infinite rotation. So if you spin this bond 180 degrees, then this hydrogen that used to be poking at you is now poking away from you. So you would never know that it went through syn addition because it immediately starts rotating and the hydrogens are going to end up all over the place. So does this matter? Does this syn addition matter for the following molecules? Well, for this one it really doesn't, because it's just going to spin away anyway and you won't even know that both hydrogens originally started off on the same side. For this molecule, it does matter. And the reason for that is this single bond is locked into a cyclohexane ring and cannot just spin indefinitely. It can ring flip, it can wiggle, but it can't spin. So these two hydrogens right here that started off via syn addition on the same side will always be on the same side. They will always be cis relative to each other, and the two methyl groups will always be cis relative to each other as well. The point that I'm getting to is that this syn addition really only matters if you're dealing with ring systems, because when you hydrogenate a ring system like this, then that ring is going to have a cis arrangement of those two hydrogens. One of the classic examples of this particular syn arrangement is in this compound right here, 1R5R266 trimethylbicyclo311-heptuene, which rolls right off the tongue. This would be a good way to name your child and then have them hate you. How do you alphabetize them at the beginning of the alphabet because they start with a number? They would hate you. So try it out and see how it goes for you. So here we have an alkene. This alkene is going to undergo catalytic hydrogenation. When that hydrogenation occurs, both hydrogens are either going to plug into the top side of this compound or they're going to plug into the bottom of this compound. If you plug both of them into the top of the compound, then you're going to end up with this product over here. Both hydrogens plug into the top, and that forces your methyl group down. That would be this product. If instead you plug both hydrogens into the bottom of the compound, because they both have to plug in on the same side, then we'd end up with this product. So one of these two is the major product. In order to appreciate this probably more fully, let's take a look at ChemDraw 3D. And so here over in the 2D window, that's the exact same compound we're just looking at. Let's identify that pi bond. Here is the pi bond that we're focusing on right here. This is the pi bond. And so when this compound docks, just like a spaceship landing on a runway, or an airplane, if you've never seen a spaceship, it's something landing on a runway. When this thing docks on that runway, it has to dock so that the pi bond system is flat. So think about this from the metal's perspective. The metal has to be either directly underneath as a platform, underneath this pi bond right here, or it has to be above that pi bond. So it's either going to be the metal up here or the metal down here. And what you'll appreciate is both sides are going to be pretty tricky. You try to put a massive metal surface on the top, these hydrogens right here are going to run into that metal surface. It's going to be hard to dock on there. So you can kind of have the metal kind of at an angle. This would dock kind of diagonally. Not ideal, but it would have to work because experimentally they observed that this does indeed hydrogenate. If instead you try to put the metal down here, what's different about this is if you kind of look at these 5 carbons, one here, see if I can get these to turn yellow for you. Yeah, there they are. That carbon, that carbon, that carbon, that carbon. These 5 carbons right here you can think about as, whoops, not that one. These 5 carbons you can think about as kind of being a flat surface. Okay? And that is the flat surface that needs to dock directly on the metal. Relative to those 5 carbons, there is a carbon poking up. That would be, we'll call that carbon number 6. And this carbon poking up the opposite direction called carbon number 7. Our original compound was a bicycloheptane, so we've just defined the 7 carbons in the bicycloheptane. Carbon number 6, which is up top, just has 2 hydrogens on it. Carbon number 7, which is on bottom, has 2 methyl groups on it. These 2 methyl groups are going to make it very hard for this molecule to dock with carbon number 7 on the bottom. So much if the metal surface is down here, these 2 methyl groups are going to make that a weird fit. So it's much more likely that the compound docks with carbon number 6 now on the bottom right here. So that's what I was trying to show here, that if we dock with the metal down here on the bottom next to carbon number 6, and both of those hydrogens get plugged in from the same side as carbon number 6, that will cause this methyl group right here to end up poking up. So because of the way that they dock and the way that both hydrogens have to add in from the underbelly of the compound, that will force this methyl group that used to be attached to a double bond up and ultimately will end up on the same side as these other 2 methyl groups. So that's why over here, now going back to a 2D diagram of this one, here the methyl group has been pushed up adjacent to the other 2 methyl groups, and here the methyl group has been pushed down away from these other 2 methyl groups. And at first glance you might think, wow, pushing it up would create steric strain, and it does, but the reason it gets pushed up is because there's a metal surface that is much more sterically encumbered than these 2 methyl groups right here. So we would expect for this compound on the left right here to be our major product. If that didn't make sense to you, I'm sorry. I know even in class this is a very difficult model to try to show students. Ultimately I ask them to break up their model kits and try to build these compounds and then appreciate it like this. I'm hopeful that ChemDraw 3D might have given you some perspective. If you do happen to have ChemDraw 3D installed, you can actually copy and paste, actually just type this name in and have ChemDraw 2D spit out the structure and then copy and paste that structure over into the 2D panel of ChemDraw 3D. You can play with the molecule yourself. Okay, new concept. And hopefully if you're asking, well, what concept did we just talk about? It was the syn addition concept. Now we're moving on to one of the things that we've done in the past to determine the stability of compounds is we've set them on fire. And the heat of combustion value was a useful way of determining the relative stability of compounds. So here is a different approach to that same problem. This is 1-butene, cis-2-butene, and trans-2-butene. These are all isomers of each other. The 2 on the right are stereoisomers of each other, and then this is a constitutional isomer of cis-2-butene and a constitutional isomer of trans-2-butene. So these are isomers of each other, and since they have the same number of carbons, if we set them on fire, we could use the heat of combustion to tell us which one was the most stable. And as we learned before, a mono-substituted alkene should be the least stable, di-substituted alkenes should be more stable, and the cis is less stable than the trans because it has some steric problems with these 2 methyl groups. That was what we learned before. Heat of hydrogenation, this catalytic hydrogenation reaction we just looked at, I mentioned that it was exothermic. If I hydrogenate all 3 of these compounds, they will all produce the exact same product, butane. And so if you can take different starting materials and hydrogenate them and get them to drop in energy so that they have now the same energy, so if I hydrogenate all of these, they're going to drop in energy until they land at the ground floor, which is the energy of butane. The total heat that is given off when these things get hydrogenated will tell me about the stability of the pi bond. So does this tell us anything new? Heat of hydrogenation can be used in the exact same way that we used heat of combustion to determine the stability of different alkene substances. Does it tell us anything new? In this particular case, no, it doesn't. In the next case, it actually does. Heat of hydrogenation does not require you to hydrogenate the entire compound. You're just hydrogenating a single pi bond. And what you'll notice is that one butene and one hexene do not have the same number of carbons. And if you tried to burn these, one hexene would give off more heat because there are more carbons. But if you hydrogenate them, then they give off the same amount of heat. And the reason for that is the heat of hydrogenation is unique to the alkene. Both one butene and one hexene have a monosubstituted alkene, and hydrogenation allows you to probe the stability of that monosubstituted alkene. So this is the cool part about heat of hydrogenation, is it now allows you to compare alkenes that are not isomers of each other. Butene has 4 carbons, hexene has 6 carbons, cis-2-pentene has 5 carbons, and yet when I hydrogenate them, this doesn't tell me about the stability of the compound. It's telling me that the double bond, the pi bond in one butene and one hexene are just as stable. They're both monosubstituted. And the double bond in cis-2-pentene is more stable because it gives off less heat when you hydrogenate that. And we expect that because it's a disubstituted alkene. The trans-2-butene is similar to the cis-2-pentene because both of them are disubstituted, but the trans-2-butene gives off slightly less energy because it's slightly more stable, because trans is generally less sterically encumbered than cis. And finally, the 2,3-dimethyl-2-butene is a trisubstituted alkene, gives off the least amount of energy when you hydrogenate it, and is therefore the most stable. So this particular heat of hydrogenation allows us to compare the stabilities of alkenes even when the number of carbons is different. So as a practice problem, now you should be able to predict the heat of hydrogenation of both 1-octene and 2-methyl-2-pentene. Pause the video and see if you can predict the heat of hydrogenation of these two compounds based on this table right here. Let's see how you did. And there's a few things I should probably fix that I said wrong. So here I've moved this table from the PowerPoint to ChemDraw, and I've drawn out all my compounds. There's 1-butene, 1-hexene, cis-2-pentene, trans-2-pentene, and 2,3-dimethyl-2-butene, and their various heats of hydrogenation. These two are monosubstituted and have a heat of hydrogenation of 126. That's what you should have expected for the 1-octene. It's monosubstituted as well, and should have a heat of hydrogenation of 126. These two substances here are disubstituted, and they average out to be 116 as the heat of hydrogenation. Did I even put units on there? I did not. Clearly, I did not care. So, let's see. No, nowhere, anywhere do I have units on that. That's embarrassing. Oh well, units of hydrogenation heat, that's what we'll call it. And so these two that are disubstituted end up being about 116. And then I said earlier that this is trisubstituted, but when I draw it out, I see that it's actually tetrasubstituted. So it's 110. So monosubstituted are about 126. That's what we see here. Disubstituted are about 116. The average, the only two data points I have. And the tetrasubstituted is 110. So I would expect this trisubstituted to be somewhere between the tetrasubstituted and the disubstituted, so I would guess in the ballpark of 113 would be a reasonable guess, just based on the pattern of the data set that I showed you. Okay, so the point of that topic was to think about the energy associated with the heat of hydrogenation and how that is another way of using experimental measurement to determine stability. But it didn't really teach us anything new. We got the same information out of heat of combustion. It's just that heat of hydrogenation allows us to also think about things that aren't isomers. That was the point. New idea. This reaction going from left to right is an E2 elimination of a secondary alkyl halide with a strong, small base. So this was a central feature of the last chapter that we looked at. We would produce propene as our major product with hydrobromic acid as an inorganic product of this reaction. Sort of. The only way you get hydrobromic acid is if you cheat. The ethoxide is the one that actually pulls off the hydrogen, and you get hydrobromic acid by the bromide ion pulling the hydrogen back off of the ethanol. So this is a bit of a lie, but it's a lie that's useful to me because it allows me to think about the reverse reaction. If instead I just run the reaction in reverse, then I can add an alkene to a halogenic acid and I can get back to my original alkyl halide. So if you want the equilibrium to produce an alkene, you add a base. If instead you want to turn the alkene back into an alkyl halide, you add the acid, the halogenic acid. And this is another example of that electrophilic addition mechanism that we're going to look at in this chapter. Catalytic hydrogenation was the first example, kind of an oddball because of that catalytic cycle instead of a standard mechanism. But this now addition of a hydrogen halide to an alkene is kind of a more classic example of this type of mechanism that's called electrophilic addition. And for the sake of brevity, I usually just abbreviate electrophilic addition as EA. And there's not like an EA1 or an EA2 like we saw with SN1 and SN2, but it is a type. So now thinking of the list of mechanisms that you know by name, there's SN1, SN2, E1, E2, and now this EA mechanism. If you run this reaction using hydrobromic acid, it is a stronger acid, so you will produce product faster. If it's hydrochloric acid, you'll actually produce product slower. And the solvent in these reactions is the same type of solvent that we would use in catalytic hydrogenation. Typically acetic acid is used. It's a good solvent, has a high boiling point, but also these halogenated methanes. Dichloromethane, which is called methylene chloride, is the common name, is probably the most common solvent that we have students use in the first semester organic chemistry laboratories. I'm just pointing these solvents out. They're not a big deal. Don't worry about them for now. Okay, mechanistically speaking, this reaction of electrophilic addition is a brand new mechanism and has new features. And the first step is you are going to take an alkene and you are going to put it in the presence of a very strong electrophile. A very strong electrophile is something that carries a large positive or partial positive charge. And this hydrogen carries a large partial positive charge because it's connected directly to a strong, this is a strong acid, so this would be a good leaving group essentially. So what we do is we mix this alkene with a strong acid and the pi bond hinges out and grabs that hydrogen. So you can think about disconnecting this pi bond either at this position and then swinging the pi bond like a door to go pick up that hydrogen, leaving it connected at that position. Or you can think about hinging the pi bond away from that carbon and reaching out and picking up the carbon. During that hinging process, you end up producing a carbocation. And so now you ask yourself, if I'm going to make a carbocation, would I want to make the carbocation at the primary position by swinging the electrons this way, or would I make it at the secondary position by swinging the electrons that way? And this arrow is drawn very suggestively, and you can see that we're going to make a secondary carbocation, and that should make sense to you based on carbocation stability. That these reactions have a strong preference to grab the hydrogen off of the acid in such a way that it produces the most stable carbocation. I'm going to say that again in a minute, and then we're going to give it, that rule is going to be named after somebody whose name is just about as difficult to pronounce and remember as everything that I just said. So repeating the rule, when a pi bond in an electrophilic addition mechanism, when in an EA mechanism, when the pi bond grabs the electrophile, it tends to produce the most stable carbocation. That particular rule is called Markovnikov's rule, and I'll show you the spelling of that in a second. If you're up on your Russian, I think that'll be pretty easy for you. So the pi bond swings out and grabs the hydrogen, it produces the carbocation. Formation of the carbocation is definitely your rate determining step. And so the rate determining step involves the formation of the carbocation. Is the rate determining step unimolecular? And the answer is no. There are two distinct molecules coming together to form that carbocation. That's the first time we've seen this. In all past examples, when we made carbocations, it was because one thing fell apart all by itself. That's why E1 was one molecule falling apart to form a carbocation. SN1 was one molecule falling apart to make a carbocation. Here we have two things coming together to make a carbocation. That's a unique feature of this EA, or electrophilic addition mechanism. Once you form the carbocation, then all hell breaks loose, and everything rushes in towards that carbocation. This chloride ion is an especially good nucleophile, captures the carbocation, and you're done. And hopefully at this point you ask, wait, that's a secondary carbocation. Do secondary carbocations tend to shift in these EA mechanisms? And the answer is yes, abso-freaking-lutely. You're going to see some carbocation shifts in these mechanisms, and hopefully that keeps you awake at night, because we still have to deal with all the shift problems that we saw before with the SN1 and and E1 mechanisms. The shift problems. I hope Google Translate or YouTube Translate gets that correct. Okay, so Markovnikov's rule. I said it the way I like to say it. Markovnikov said it a different way. The way I like to say Markovnikov's rule is your carbocation is going to form at the more stable position. What Markovnikov realized was, well, the carbocation, we actually know it's there because that's where the halogen landed. So he says that the halogen adds to the more stable position. That's the more substituted position, and that's because the carbocation formed at the more substituted position. So it's 6 of one, half dozen of another. The way Markovnikov states the rule is that you're generally going to add your halogen to the more substituted carbon. This is a good rule to remember because we're going to spend a lot of time debating between the Markovnikov addition of a halogen and the anti-Markovnikov addition of a halogen, where it adds to less substituted carbon. But for now, that complexity does not exist in your life. All halogens add to the Markovnikov position until tomorrow. So why? Well, when you think about that alkene, now perhaps this slide is not as helpful as the previous one. The truth is that the electrophilic addition involves the distinct formation of a carbocation. And we spent quite a bit of time thinking about carbocation stability, and it tends to show up at the more substituted position. Because the carbocation shows up at the more substituted position, that's where the halogen ends up, and therefore Markovnikov's rule states that the halogen adds to the more substituted carbon. Me repeating things over and over again. I'm going to move on. So let's look at one more mechanism, and this is the reaction of 3-methyl-1-butene with hydrobromic acid. And this is an electrophilic addition reaction. You should recognize this because it's the addition of an alkene to a halogenic acid. I don't have a fancy table for you in this chapter. I have something much more fancy. And we're going to see that in a few days, and it has been affectionately called the Wheel of Doom. So we'll get to that later. But this first reaction is simply the alkene reacting with the hydrobromic acid. And mechanistically, the pi bond is going to hinge out and go pick up that hydrogen. By hinging, what I want you to think about is the pi bond stays connected to one of these two carbons and disconnects from the other carbon. It is going to disconnect from whichever of these two carbons is more substituted. So I'm going to open the door such that my door handle is on this side, and I'm going to swing the door out away from the secondary position and reach that door around until it grabs the hydrogen. So I probably should have shown this mechanism a little bit more usefully, but what I'm trying to show here is that the pi bond swings all the way around and grabs that hydrogen, and we end up with the carbocation at this position. This is not a very helpful diagram because that hydrogen right there is not the one that I just added. The hydrogen I just added is actually down here. And the reason I'm showing this hydrogen is because now we have a secondary carbocation, and every time you have a secondary carbocation, it has a tendency to undergo a shift. So this hydrogen off of hydrobromic acid will technically add down here on this carbon. The reason that I'm showing this hydrogen is so that you can be prepared to draw the hydrogen shift that is definitely going to happen in the next step. This is a secondary carbocation. The hydrogen will shift to produce a tertiary carbocation, and now the bromide attacks that carbocation to give you your final product. Here we have a total of 1, 2, 3 elementary steps. If you go back to the first time I showed you this mechanism with propene reacting with hydrochloric acid, notice how it only had 2 of these elementary steps. The reason that this one has 2 elementary steps and this one has 3 elementary steps is because of the carbocation shift. So I wanted to make sure to show you an example that involves a carbocation shift. Here's our major product, and we're done predicting the formation of the major product. But what about minor products? Well, there's a couple of different minor products that we have to be concerned with. The first of these minor products would be what happens if the bromide came directly in and smacked that carbocation without allowing the shift to occur. And that happens. Bromide ions are very good nucleophiles, and they will react very quickly. The hydride over here is directly connected to the compound, and the bromide is not. So we expect that something that is tethered to your molecule is going to do the shift towards the carbocation before some external ion will actually capture that carbocation. Imagine that it's your life goal to run over an animal with your car. Let's choose something that nobody likes, a kitten. So if your goal is to run over a kitten with your car, it's much more probable that you will accomplish that evil goal if the kitten is directly tied to your vehicle versus some random kitten that's not directly connected to your vehicle. So that's the principle, the analogy that helps us understand why an internal hydride shift will most likely beat the bromide in moving over to that carbocation. So this would be my major product shown in black and the minor product shown in red. In this particular example, I don't have other products. That's right, that was the review quiz where we saw all kinds of products forming. This one's a little bit more straightforward. This is the major, this is the minor. What would happen if instead of using hydrobromic acid, I used hydrochloric acid in this reaction? Well, this first step is the rate determining step. And the first step is acid-base chemistry. It's not often that we see acid-base chemistry as the rate determining step, but that's because we made a carbocation right here. Acid-base chemistry is faster or slower depending on the strength of your acid. Hydrobromic acid is stronger than hydrochloric acid, so that means that hydrobromic acid would react faster than hydrochloric acid in this first rate determining step. Bromide is also a better, faster nucleophile than chloride, which means that while we expect the hydride shift to win, the bromide, it's a closer race. So if, let's say, that 80% of the compound went this way and 20% of the compound produced this minor product, then if I switch it out for chloride, hydrochloric acid, where chloride is a slower nucleophile, we would expect for even more shift to happen. So instead of being 80, it'd be like 90% and then 10% here. So the principle to take home, and what you want to write down in your notes, is the more reactive species is less selective. It's kind of more random in terms of how it does the chemistry. A less reactive species, like hydrochloric acid, is more selective, meaning that you're going to get a better yield of your major product. So hydrochloric acid actually is a little bit better in a lot of these reactions because it's slower and it waits for everything to shuffle out before it comes in and attacks the carbocation. The last thing that we want to do is show an energy diagram for this reaction. So I'll start with my coordinates right here. There's my reasonable coordinates. There are 1, 2, 3 elementary steps in this reaction. So I'm going to start off at some arbitrary energy level. My first step is my rate determining step. So I need to go uphill to my carbocation. Then I see a hydride shift. Usually that has a small activation barrier and produces a minimal improvement in the energy. And then the bromide is going to come along and capture this. We're assuming this reaction is spontaneous. So I need to end up lower than where I started. So this is kind of a waterfall in reverse. You push the water up and then it kind of just rolls down the hill. So 1, 2, 3 total elementary steps, with the first step being the rate determining step.